This video will eliminate the disadvantages of this type of greenhouse. Like this Dutch greenhouse, which is heated with this large number of solar collectors in winter. When the sun is shining, these solar collectors heat more than 1,000 tons of water in this tank, up to a temperature of 680 degrees Celsius, and then, in the evening or at night, that thermal energy heats the greenhouse through water radiators. Now I am showing examples of other greenhouses of this type. Unfortunately, this type of greenhouse heating has the following two disadvantages. Firstly, solar collectors cannot cover 100% of the heating needs of greenhouses, and therefore they must have cogeneration systems or heating boilers based on natural gas or other energy sources. The second disadvantage is that more than half of the thermal energy of solar collectors is thrown away, and therefore their energy is too expensive. Those two disadvantages are explained by this graph of heat production by solar collectors during 12 months, when this production in winter is several times less than this production in summer. At the same time, these heating needs of a greenhouse are required only in winter, at the end of autumn and beginning of spring. Obviously, we must throw away this thermal energy of solar collectors, and we must cover this heating deficiency with those boilers. Of course, many of you have already come up with the idea of storing this excess summer energy during several months in order to use it in winter to heat greenhouses, and this solution eliminates those two disadvantages. Therefore, I remind you of this successful example of the transfer of thermal energy from summer to winter, when the heat transfer fluid of these solar collectors heat the soil through these pipes to almost 880 degrees Celsius during the summer months, and this soil temperature remains during several months until winter, when the hot soil heats the water through the same pipes, and this thermal energy is used for space heating of approximately 50 houses. Unfortunately, this heat storage loses about 50% of the thermal energy due to these heat leaks, but now I will start showing a project for heating greenhouses, when our heat storage will lose only 20%, and the greenhouses will be heated only by solar energy without any boilers. In addition, the cost of solar energy will be significantly cheaper than heat from natural gas or other energy sources. It will be a project for heating greenhouses with an area of 10 hectares. Our summer thermal energy will be stored inside an artificial mountain with a volume of 500,000 cubic meters and with these dimensions. In summer, this mountain is heated to temperatures of almost 300 degrees by a large number of mirror-type solar collectors, which will be described in 7 minutes, but we are not heating all 500,000 cubic meters of the mountain, but only this hot zone with a volume of 350,000 cubic meters and weighing a little more than 500,000 tons of dry soil. And this remaining soil is a layer of thermal insulation with a thickness of a little more than 5 meters, which resists heat losses in these directions. This layer of soil with a thickness of 10 meters between our mountain and these groundwater resists heat losses in these directions. Of course, many of you have already understood that we will locate almost 1 hectare of greenhouses here, on the horizontal top of our hot mountain, and it is obvious that these heat leaks from the mountain are not lost, but heat our greenhouse. The power of these heat flows is shown in this graph, and this is the heating requirement of the greenhouse from October to April. We understand that this thermal energy, outside the heating season, must be released into the atmosphere, and this is a heating deficiency, which should be covered by heating the greenhouse through water radiators or some cheap unconventional methods of moving thermal energy from inside our hot mountain. It is also interesting to look at this flow of thermal energy from the hot mountain at the end of summer, but we see that this heat will not cause a big problem because it is approximately 5 times less than the heat which comes inside the greenhouses directly from the sun in the summer, and which also requires removal from the greenhouses. Also, many of you understood that we will locate almost 1 more hectare of greenhouses here on the southern slope of the hot mountain, similar to these solutions. The big advantage of this arrangement is that such greenhouses receive noticeably more solar radiation, and several times more on a sunny day in winter. It is obvious that this greenhouse is heated by these heat losses from the hot mountain, and the features of its heating are the same as for the greenhouse that was just described. Thus, we have placed 1 hectare of greenhouses here, and another 1 hectare here, But the remaining 8 hectares of our greenhouses should be built outside the hot mountain, and let's look at how they will be heated. Here we install a large number of pipes for thermal oil, which takes the thermal energy of the mountain and transfers it through heat exchangers to the water that circulates through the heating radiators of the greenhouses. Obviously, the same oil is used to take thermal energy from the solar collectors and transfer it to the soil of our hot mountain through the same pipes. The diameter and total length of all those pipes should be sufficient for the oil to transfer heat with a thermal power of up to 50 megawatt when the temperature difference between the oil and the soil is 20 or 40 degrees, but it was the condition for a sunny afternoon in early autumn. But for example, April or May requires the work of only 40% of the pipes, which should provide the same 50 megawatt with the temperature difference of about 80 degrees. These videos of my first YouTube channel described other features of the operation of those pipes, and the link to it is below. Let's pay attention to these side slopes of our mountain, and we understand that their surfaces will be covered with various pipe connections and valves. We also understand that here, on the side slopes, we must place a layer of thermal insulation with a thickness of about 1 meter to resist heat losses in these directions, and it could be mineral wool, foam insulation, or other cheap material. I remind you that those pipes do not fill all of these 500,000 cubic meters of our mountain, but only these 350,000 cubic meters of the hot zone, whose maximum temperature is reached in October, when the center of the hot zone has a temperature of 290 degrees, but the temperature of the periphery of the hot zone is slightly lower, 240 degrees. But in November, December and later, we take the heat for our greenhouses through these lower pipes, while thermal energy from the solar collectors comes through the upper pipes. These actions lead to the fact that the boundaries of the hot zone gradually move upward, and this fact leads to an increase in the thickness of the layer of this soil thermal insulation, which is additional thermal insulation to these 10 meters of soil between our mountain and the groundwater. Increasing the thickness of this total thermal insulation reduces these heat losses in the downward direction, and those heat losses are also reduced due to the gradual decrease in this temperature at the periphery of the hot zone. Now, I remind you of the situation in mid-October, but this is the situation in mid-November, and these heat losses are reduced by 20%. This is mid-December, when the thickness of this layer increases to 3 meters. And these heat losses decrease by 1.5 times compared to October. January increases the thickness of this layer to almost 5 meters, and February increases it to 6.5 meters, and this temperature is almost 2 times less than it was 4 months ago, and these heat losses are 3.5 times less compared to October. Now let's look at this heat loss through the north side of the hot mountain. Here we put a layer of additional steel pipes, but not for that hot oil, but for the hot water that circulates between these steel pipes and the heating radiators from October to April. So, the thermal energy of this layer of soil is transported inside the greenhouses, and this action leads to a radical decrease in the temperature of the soil near the pipes, below 100 degrees. This decrease in soil temperature leads to a decrease in these heat losses by approximately 2 times if these pipes are located at a depth of 4 meters from the surface of the mountain. Of course, we can also install similar pipes here, 6 meters above the groundwater, that is 4 meters below the natural ground level, to further reduce these heat losses, but I won't use this solution because it requires additional excavation work. And 2 minutes ago I showed how we already reduced the heat loss downwards. We can understand that the temperature of our mountain will reach its minimum in March when we face this situation where the soil stores only a small reserve of heat for the event of an abnormally cold winter. After this, the flow of thermal energy from the solar collectors will begin to exceed the heating demand of the greenhouses, and therefore the temperature of the mountain begins to increase. April and May require the hot oil from the solar collectors to be directed only through these 40% pipes in the center of the mountain, and these actions form this hot zone when the thickness of this layer of soil thermal insulation is more than 10 meters, and these temperatures of the periphery of the hot zone are low, and therefore these heat losses are small. But subsequent months require an increase in that percentage of the pipes, and this leads to a gradual increase in the size of the hot zone and a decrease in the thickness of this thermal insulation layer while this temperature increases, and therefore these heat losses increase rapidly. In September and October, the hot oil from solar collectors goes through all 100% of the pipes, and those heat losses are the greatest. This is my calculation of all those heat losses from the hot mountain in all directions during the 12 months. And it is interesting that the heat losses during these 4 months, from July to October, are greater than the heat losses during the remaining 8 months. I also remind you that these heat losses through the southern slope of the mountain and its horizontal top are not lost from October to April, but go inside the greenhouses and heat them. Of course, we can heat our mountain with these expensive solar collectors, and for example, these mirror systems heat thermal oil to a temperature of 393 degrees. These systems use a more expensive heat carrier, namely molten salts, which are heated to almost 600 degrees, and this type of mirror systems heats the heat carrier to the same temperatures. This type of mirror systems is capable of heating a heat carrier to even higher temperatures, and now I am showing their analog, where not a concave mirror is used, but a Fresnel lens, which focuses solar radiation on this spiral for circulation of heat transfer fluid. Unfortunately, these systems may be too expensive for our greenhouses, and therefore I remind you that I wrote below the link to my first YouTube channel, which explores a variety of low-cost mirror systems that are many times cheaper than those expensive mirror solar collectors. These cheap mirror systems are designed to heat water or thermal oil up to 300 degrees Celsius. Our hot mountain must be heated by this amount of cheap mirror systems, 120,000 square meters of mirrors, which should be located on approximately 25 hectares of land. In addition to 3 hectares under the hot mountain and 8 hectares for the greenhouses outside the mountain. Of course, a large area of land for the solar collectors is a problem. But we can remember that such land is often used for sheep, bees or other agricultural purposes. This is the annual production of thermal energy by that amount of cheap mirror systems, and we see that this heat production during 6 months around summer is 2.5 times more than this heat production during 6 months around winter. This thermal energy is the heat losses from the hot mountain. And these 22 million kilowatt-hours of heat come into the hot mountain from April to September and are stored there during several months, and then they heat the greenhouses. These 11 million kilowatt-hours of heat are produced by those mirror systems during the heating season of the greenhouses, and therefore they come to the hot mountain to quickly leave it to heat greenhouses, but these 3 million kilowatt-hours will be lost in the heat losses from the mountain. Here I have shown an approximate forecast of the total costs of building 10 hectares of the greenhouses, 120,000 square meters of those cheap mirror systems, and the hot mountain for 500,000 cubic meters of soil, and we see that the solar collectors and the hot mountain increase the cost of greenhouses insignificantly. In addition, we can add this cost of those 36 hectares of land at average prices in the Netherlands, but this is a real estate investment that has a radically lower risk and cost of capital, and also I remind you that the main part of the land can be used for agriculture. I have described the project for the climate of the Netherlands or neighboring countries, and now I am showing this example of the climate of Amsterdam for comparison with this example of the climate of the northern United States. We see that the American climate has colder and sunnier winters, and a longer heating season. And therefore it is clear that the number of mirror systems, the volume of the hot mountain and other parameters for American greenhouses may be noticeably different. In addition, American winters can be snowy, and this fact will reduce the heat production of some types of mirror systems. I also remind you that it was a project for 10 hectares of greenhouses, and the smaller the area of the greenhouses, the greater the percentage of those heat losses and the worse the profitability of the solar heating. I think everyone understands that our ideas are not suitable for a small greenhouse because of the complexity and because they will have a catastrophically high percentage of those heat losses from the hot mountain. Interestingly, the hot mountain can not only provide thermal energy, but also produce electricity using a turbine. These possibilities for the simultaneous production of heat and electricity are described in this recent video from my first YouTube channel, the link of which is below. In addition, I remind you that the hot mountain use the pipes that lie parallel to the west-east line, but the pipe system may be different. For example, it may consist of similar pipes, whose inlet and outlet are located here, in the greenhouse, or it may consist of pipes that run along all four sides of the mountain,